Good day, everyone. Today we'll speak about electrophilic addition mechanisms. Okay, so the first example we're going to go over is just a simple electrophilic addition with a vinyl or 1-butene, okay, coordinating to a hydrogen, kicking a bromo group off. So the HBr is going to be the electrophile in this particular case, so electrophilic addition. Okay, so you have two options in which you'll have that hydrogen amend. The first is, so these hydrogens that I've indicated here are no mistake. Okay. Typically they're going to be assumed, in just regular line structures. But just to demonstrate, you're going to have two different carbocations. Okay, so which one do you feel is going to be most stable? Well, if you recall, secondary is going to be more stable than a primary. So in other words, you're going to see this secondary carbocation form. Remember, you need to account for the octet rule. Okay, so now seeing as this carbon has a deficiency, so we have Br minus, it's on the wing here. Okay, it is going to coordinate readily with that carbocation carbon, and you're going to get a mixture, a racemic mixture of R and S. Racemic mixture. Okay. So this is what is referred to as Markovnikov's rule. Markovnikov's rule states that hydrogen is going to go to the hydrogen upon an alkene that has the most hydrogens attached to it. So in other words, in this position, and then the attacking group will amend to the most substituted carbon, which is in fact the secondary carbocation that you see right there that gets generated. Okay, so that's Markovnikov's rule. We'll get into an example of anti-Markovnikov addition when we get into radicals in chapter 25. Okay, so let's now think of resonance for a second and see if the same thing will play out with an aromatic benzene ring. Okay, so these are all cis double bonds, so you think, well, it should be fairly reactive, maybe not as reactive as, say, a vinyl group. However, remember that these electrons are constantly going in motion, right? So they're constantly resonating about this sp2. These pi bonds are bouncing around upon this sp2 construct here. Okay, so therefore, these lone pair, or these pi bonds can't reach out to an acidic hydrogen and coordinate to it. So in other words, it would break up resonance. So it's almost like trying to break off, let's say a circuit of some kind. You would have to physically separate that out in order for the flow of electrons to stop going. Okay, so in other words, this is not going to react. This will be effectively inert. And we'll get into substitutions of aromatic compounds later on in the course. Well, actually, next semester, you'll see plenty of examples of that in electrophilic aromatic substitution. Okay, so let's think back to what I was talking about with secondary and tertiary carbocations. So those are going to form the most stable compounds, intermediates the fastest, because you're going to have some kind of carbocation intermediate, right? So if we look at problem 11.23 in your text, we think of, say, tetrasubstituted, which is going to form almost stable carbocation, right? So let's just say A for generic acid, whatever that is, okay, and form its conjugate base from acidifying. Okay, so one of these is going to be tertiary. Okay, so it's going to be very stable. Right? Now, you'll see another example, say here with this tetrasubstituted substrate. Now, remember that you have resonance stability once this carbocation is formed. So, okay, so we've added H plus to it. So let's say carbocation's right here. Just put pH right here. So remember that pH is going to stand for a phenyl ring. So a phenyl ring can resonance stabilize this positive charge even more. Okay. So in other words, this is probably going to be even more stable than what you see right here. In fact, it's going to be objectively more stable because of it resonating with, remember, that phenyl group that is going to be okay. So the other two examples that your text has for that particular problem are just ethylene or ethene, whatever you want to call it, and then this particular trans double bond. It's on the opposite side here. So this is going to be the least stable, therefore it's going to react the slowest. Okay, so remember, you want to have some kind of stable intermediate for things to proceed forward. It's not so much a stability of being the intermediate itself, it's actually getting to there being an intermediate. Okay, so that's pretty much the first step you have to think of in terms of proton transfer. Now, proton transfer is going to happen relatively fast, but in this case, instead of having lone pairs from electronegative elements that are reaching out to these H plus nuclei, now we have pi bonds that are reaching out. So it's going to be a little bit slower of a process trying to protonate this than protonating either one of these. So the general order is this is going to be slowest. This is going to be second slowest. This is going to be second fastest, and this is going to be the fastest. Okay. All right. So problem 11.30, I want you guys now to think about what effect low temperature and high temperature are going to have. In other words, what's a kinetic product versus a thermodynamic product. So remember, with thermodynamic products, you're going to use heat to drive that product formation. Okay. Now, a couple things to think about here. So we'll have this substrate with HCl. Okay. And then we'll say this is at 0 degrees C, and this is with heat applied. Okay. So this is going to be Not necessarily a slower reaction, but you're always going to have the same beginning step, right? So at low temperature, you're going to have the secondary carbocation, and you're just going to have the fastest form product take place. Okay? So negative to positive, and you have your R and S mixture. And get out of the way, man. Jeez. Okay. Then we have our other conditions. So we have higher temperature with our heat applied. Okay. So same step as the first time. So we're going to have our carbocation intermediate. Okay. Now, if we have additional energy applied, we can go to a more thermodynamically stable carbocation. Okay. We're going to have a hydride transfer to a more stable carbocation via resonance, right? Because it can resonate with this double bond. Okay, so then if we have Cl minus, again, kind of hanging out, waiting to coordinate with a positive charge, then we're going to get a mixture products. So that extra oomph is going to basically initiate that that hydride transfer before coordination is going to take place. Sorry if you can't see that. There we go. That's better. All right. So different products depending on what type of temperature or heat is applied. Okay. So on the top, you're going to have a kinetic product. On the bottom, you're going to have a thermodynamic product. Okay. On to electrophilic addition of alkynes. So if you have HCl in excess, that is going to substitute not once but twice at this particular carbon. Remember, you're going to have a carbocation intermediate, best situated right there, alpha to the ring itself. So in other words, you're going to get a disubstituted or dihalide product like so. It'll be not stereospecific. Okay, so there may be some other kind of functionality you could use with this further down the road if you're trying to do some kind of synthesis. All right. I'll get into hydration of alkynes in a little bit, but let's go over some simple forms of hydration here. One in particular. So we have, say, this trisubstituted trisubstituted alkene, and we have water in the presence of acid. Okay. So what's going to happen is this double bond is going to coordinate to H plus and form a conjugate base from this acid. Okay, so what is going to be the most stable carbocation intermediate, the most substituted? So in this case, water is going to coordinate and say maybe a second water equivalent is going to be around to work as a base. And you're going to get your product. So in other words, you've put a H and then OH, the most substituted carbon. So this will be your product. Not stereo specific. Okay. So let me erase this alkyne here and go over another instance of hydration. Now, instead of using just regular old water, you can use acetic acid, you could use some kind of alcohol. So if you remember the previous module, or at least VA, you might have remembered at the end, or you may recall at the end of the module or submodule when I was talking about ring formation. With an alcohol. This is somewhat similar, though a little different. Okay, and of course you're going to have H plus around. This is just going to be shorthand for H2SO4. I understand that's an acid. Okay, so okay, so once again, a tertiary carbocation. And then acetic acid is going to be a poor nuke, but a nuke nonetheless. It's going to coordinate there. Sorry, this should not be a double bond, it's a single bond. Okay. And then it's just a matter of something taking up a hydrogen there. So let's just say a little bit of water is going to be there to serve as a proton transfer. Okay. So then you're going to have your product. So this should be RS because you have an asymmetric ring here. So just imagine this squiggly line, R and S mixture. The next one that I have in your notes you can check out and try on your own. Again, I would take a look at that that particular example that I have with synthesis from the previous submodule, and you can work with that. So that equation is like so. So instead of water, you have ethanol, and H plus again. So see what you come up with there, and if you have any questions, be sure to stop in for office hours, and I can kind of guide you through that. Okay, so now we're going to go back to that alkyne substrate. We're going to hydrate it. Say just with H3O, just be generic and as straightforward as possible. Okay, so you have an intermediate which isn't terrifically stable. Okay, positive charge about an alkene is going to be kind of a tough sell, but it is going to be most stabilized from this phenyl ring nearby it. So if we have that water now, which can coordinate. We're going to have conjugate acid of an enol. This gets picked up by another thing of water. So it's going to form an enol. Then it's going to revert to a more stable, so we're going to say proton transfer. So, in other words, this hydrogen is going to get removed and get replaced over here to where you're going to have a more stable ketone form. Okay. Now you think, well, why doesn't it just do a second OH group right here, or amend a second OH group here? Well, that's going to be an issue, because if you have two oxygens that are about a carbon, it's going to be really unstable unless one of them is doubly bound. So, in other words, two oxygens pulling off of electron density from the carbon is going to be highly unstable, no matter what the species. Okay, so just a word of caution there. Don't get tempted to think that you're going to hydrate the alkyne twice to make a diol or something like that. It's just not going to work. All right. Okay, so we'll see some other examples of hydration of an alkyne later. But let's do a little bit of review here before we get into hydration of, well, before we go back to some review examples, let's try to envision what we would use to form phenylacetylphenone. Okay. So something an alkene has to be, or alkyne rather, has to be here in order for this ketone to form. Well, most likely substrate you would have is something like this diphenyl ethine, right? 1,2-diphenylethyne as your substrate. So in other words, it's going to hydrate just once, going to an enol form, and then reverting to a keto tautomer, which is more stable. Okay. Okay, so I'm going to attempt a couple of problems here for you from the text to serve as a little bit of a review. So 11.29 on page 596, you have an enol ether. Enol is different than an enol ether here. This is the ether group right there. Reacting with HCl. Okay. So not unlike the initial step from most alkene electrophilic additions that you see. Where is the positive charge going to go? Well, remember that oxygen is right there. It has a lone pair to lend into a positive charge, so the positive charge would be most stable, is going to be right next to the oxygen. Seems somewhat counterintuitive, seeing as oxygen is going to be electronegative, but as a lone pair it can bond for a little bit, right? So whoops. I guess it's the same, but okay. So this oxygen's positively charged, but now everything has a full octet in that particular form. So this is going to be the strongest resonance contributor. Now, being that the positive charge was originally here, that's where you're going to see some kind of site. Remember, the addition is going to go about the carbon. So a chloro group, Cl minus, that you had, is now going to coordinate here. Right? So in other words, that hydrogen that originally protonated the alkene is going to be at the bottom. And you're going to have a chloro group. And again, this is going to be R and S because you have a difference about the ring. It's not symmetric with relation to where that carbon center is. Okay, so that's going to be the product that you would form in 11.29. 11.36. It's going to be similar, but it's going to be an intramolecular reaction. So this will not be unlike what you saw, again, from that synthesis example from the previous module, module VA, the end. Okay, so this lone pair, I'll just put HA as generic for, sulfuric acid, whatever. So we're going to have coordination here. Okay, and then what's going to happen? We're going to form a most stable carbocation at this end. So in other words, what we're going to see is positive charge right here. Lone pair coordinating. We'll continue to have a positive charge. So again, under acidic conditions, you're following positive charges. Okay. So 1, 2, 3, 4, 5 membered ring. That positive charge right there. Okay, so this is going to be very acidic. So let's say water or some kind of generic base is going to be around to pick that up and have a stable ring as a product. Alright, so now we're going to talk about three-membered three-membered ring formation, either intermediate or final product. So the first we'll start off with is carbenes. So let's just say we take 2 propene, react that with some kind of carbene like so. So a carbene is going to be sp2 hybridized. It's going to have 1 pseudo coordinate, 1, 2, 3 total coordinates. And things are going to be concerted. So what that means is a lone pair is going to coordinate on the same side about that alkene, and then the double bond will come back and coordinate to that carbon. So you're going to form something that looks like so. Okay, so you're going to form a strained 3-membered ring. Okay. So there's going to be some stereospecificity. In this particular example, not so much. But if you had something that was more substituted, let's say if it were trans in this case, then you would see a wedge going into the plane of the board. So, in other words, you want to get a three-membered ring that's all about the same plane, same XY sort of grid or plane, and then have your substituents either sticking into or out of that particular plane. Okay, so there are two ways in which you can generate a carbene. First being through, say, diazomethane, just to form, let's say, a methylene group right there. You would use light, high intensity light, like UV light, so it's going to be strong, and it's going to cleave that CN double bond to where you're just going to form a two singlet carbene intermediate. Okay, so it's going to be generated in situ, again, in the situation. Okay, now another formation of carbene, if let's say you wanted those R groups to be a halide, you would treat, let's say, chloroform, which is going to be very mildly acidic. Right? And use a strong bulky base like butoxide to remove that hydrogen. Okay. So this is going to be sort of an unstable carbanion, even though these are electron withdrawing. But the more stable form would be a Cl minus. Remember, it's going to be a full octet. And you're going to have this carbene as a result. That Cl minus getting kicked off. All right. So this is going to react in the same way that you've seen here. So in other words, this carbene should look something like so. Again, it's going to be a concerted mechanism. It's going to either happen above or below the plane of the double bond. Okay. Next example I'm going to show you is just going to be a three-membered ring intermediate. So you're going to form a brominium cation. So it's either going to be positively charged or neutral in terms of three-membered rings. In this case, it's going to be positively charged as an intermediate, but neutral once that ring is popped open. Okay, so if you recall back to when I was introducing dash wedge notation to you, so you take cyclohexene, reacting it out with Br2. So this is going to be electropositive, this being electronegative if there's some instantaneous dipole. Okay, so then one of these lone pairs is going to come around and snap back to one of these carbons. So you're going to have this brominium intermediate, and that bromo group that got kicked off, while not the world's most exciting nucleophile, could come around and break off either one of these bonds And you're going to have a syn addition at either case. So in other words, you are going to have a stereospecific product, right? But one bromo group is going to be into the plane of the page and one is going to stick out. Okay. Now, if you were to treat this with water, you're going to form a halohydrin. So this is going to pop over in the ring. Again, not the world's best nucleophile. So this sticks out of the plane of the board, page, whatever. This other bromo group got knocked down. Okay. You're going to have protic hydrogen here that's just going to get stripped away from another water molecule, and then you're going to have a halohydrin. Again, it's going to be anti-addition. Okay. Now, if you treated this with base and heat, it's going to self-react. You're going to get an epoxide, if you recall, from a halohydrin intermediate. So, in other words, this is going to deprotonate this alcohol, and that O- is going to come in and attack and boot off that Br, and you're just going to have your epoxide there on the other side of the ring. Alright, so I mentioned epoxide formation before. This is another approach in which you can take. Alright, now this is going to happen in a concerted mechanism like before, just much more elaborate. So there's going to be quite a series of electron pushes here. First, you're going to have this OO single bond kind of sever. That's going to be the weakest bond. Okay, and as a result, it's going to push these electrons around. And this is going to coordinate to this hydrogen. So if this becomes if this becomes positive from removal of these electrons, something has to coordinate in the meantime. Okay, so it's going to make this slightly more acidic by this concerted reaction going on with the styrene substrate. Okay, so you're going to see this formation. Okay, now as a result, you'll also see metachlorobenzoic acid as a byproduct. So if you wanted to test to see how this worked, mechanistically you can't really prove or disprove much in terms of what's been pushed around in terms of electron arrows. However, one thing you could do is, let's say, isotopically label that oxygen or have something that's already labeled as such. That way you could kind of follow things through some nuclear means. Okay, so in other words, this is just going to be a byproduct. So you need at least one equivalent of MCPBA. So this is MCPBA here up top. Okay, so that's going to be a somewhat stable three-membered ring. Okay, so it's going to be an epoxide formation. The last thing we're going to go over today is hydrations. So hydrations of alkenes and alkynes. Okay, so the first we're going to look over is, say with an alkyne, we treat this with water and acid, H2SO4, what have you. Remember, you're going to have that enol intermediate, and that's going to revert to the ketone product, which is just going to be acetone. Okay. Now, we're going to see some examples in which you can control where that oxygen is going to go. Okay. So, for instance, if you have an alkyne and you treat it with this bulky borane group that's stabilized by THF. So that's the first step. And then the second step, you're going to be using H2O2, which is peroxide as well, NaOH, H2O, so conjugate acid base pair. You're going to actually get anti-Markovnikov addition. Okay. So you'll get propanal instead of 2-propanone, or propane 2-on. Okay? So for Markovnikov addition, you would just use things, or just acid-assisted hydration. Again, OH plus hydrogen on the end, right? So this is a Markovnikov addition, reverts to a ketone product. This is going to revert to an aldehyde because this boro group is actually going to amend at the terminal carbon. Okay, and I'll show some more specific examples of that with alkene substrates. Okay, so you would see an enol intermediate or precursor that would look something like, say, this. Okay. Now, there's a specific reason why I'm using these isoamyl substituents, because they're going to be so bulky and you already have those alkyl groups there. That's going to be important when we look at sort of the nuts and bolts of the mechanism further down. I'm not going to go get totally into the mechanism. I've already referenced the pages for those. So from 625 to 629, you can find the hydroboration oxidation mechanisms. Okay, so continuing on with anti-Markovnikov discussion. The intermediate that you're going to form from this first step is going to be hydrogen, boron there at the end. Okay, so eventually what's going to happen is you're going to have not one, but 3 coordinates about this boro group. So in turn, you'll really have something like this. Remember that boro is in group 3. So in other words, carbon's slightly more electronegative. So it's going to have a chance to coordinate with boron like so. And we'll have H2 here. So 2 more times. Okay, you're going to get that trialkyl borane intermediate. Okay, and then this portion where you're reacting out with this trialkyl borane with an oxidative species like peroxide, you're going to in turn generate 3 equivalents of, alcohol. Okay, so N-propanol from propene. Again, anti-Markovnikov addition. I didn't go through everything in terms of mechanisms. You can take a look on page 625 through 629 for that whole elaborate mechanism. I just wanted to show you guys just sort of the nuts and bolts, quick and dirty application here. Now, if you tried to do that with an alkene, or an alkyne rather, with BH3, you're going to get a mixture of products, okay? So with that said, you're going to get a little bit of alcohol like you see right here. You might see, aldehyde, something of that nature. So you're going to get a mixture. You're not going to get anything specific in terms of a target. So in other words, this is going to produce primary alcohol. And also just bear in mind here, when I say 3 equivalents, we're not creating something out of nothing here, right? We have to actually take 3 of these in order to form this boroalkyl intermediate. Okay. Now, back with the previous example when I was treating an alkyne. All right, I had this example here. Okay, and then this is just going to be with THF. Okay, so the THS is just to stabilize it. Okay, and then H2O2. I got it right today. Okay, conjugate acid-base pair of water. For the second step, again, for the oxidation step, so it's going to substitute where that boro group is. And as a result, you're going to get propaldehyde. Okay, so watch your starting material, right? So in other words, your substrate is really going to tell you what kind of product you're going to get based on these kinds of conditions. Again, you don't want to use BH3 to have an intermediate step. Also recognize here that there's just this one hydrogen. Okay, so in other words, it's going to place it right here. That boro group is going to coordinate right there at the terminal end, and then do what it needs to do, further along with oxidation, etc. So in other words, you're not going to have this trialkyl intermediate as a result, because you already have 2 other alkyl groups attached to that boron. Okay, the final hydration option I'm going to show you is one where, so we've gone over Markovnikov, anti-Markovnikov. Now we're going to go over an example in which if you're trying to, let's say, hydrate an alkene, but you don't want any rearrangement, you would use so this is acetate OAC. Okay, I think H2SO4. Okay, and then you would follow this up with what is it? NABH4, which is going to be reducing agent, and then ethanol. So what that's going to do is actually place the oxygen where you would expect if you didn't think of this hydride shift over here. Okay. So remember that both of these are going to be tertiary if you form a carbocation either here or here. But this is going to be more stabilized because that phenyl ring is going to resonate with that carbocation. Okay. So just to kind of walk you through this real quick, the intermediate that you're going to see here is one of these acetate groups is going to leave as you do this three-membered ring intermediate. Okay, so this is an acetate group that's hanging off. And this is going to be positively charged. Okay, so it's going to be an intermediate. However, it can't shift anywhere, right? Because this hydride can't slide over and kind of bump it out of the way. So in other words, this is going to be attacked or broken off from OH, or H2O, and then you're going to have that substitution as intended without the hydride shift. So oxymercuration reduction. So the second step is simply reducing everything down. That's going to ensure that there's no carbocation rearrangement. No carbocation rearrangement. Okay. All right, so again, this is just the intermediate. The final product is what you're going to see up there on the right-hand side. So that's the difference between all the different hydration reactions that you're going to see. If you have any questions, be sure to visit me during office hours virtually, and I'll try to get them all sorted out. We can go over some other examples as well if you wish. All right, everyone have a good day. Take it easy.